we left the other day, we were talking about the shift reduce parsers. And if you recall, this is a very simple algorithm, and it doesn't work on ambiguous grammars in terms of, let's say, any given CFG. If it is ambiguous, meaning if you have two possible interpretation or two possible parse trees using a left, let's say, derivation and right derivation, you might check that. And if that is the case, then you have an ambiguous grammar. But we also said this algorithm might actually also fail or give conflicts, what we called before, give conflicts in cases, in the cases where you don't have an ambiguous grammar. And the idea was basic. You use a very simple stack, and the implementation starts from the left to right scanning of your input, and you have two major actions and two minor ones. The major action is you either let's say shift or reduce, or you give an error, or you give a success. So these are the actions. And a shift is when you have an input, let's say, when you, the shift says what you can do is you can take your input. So if this is my input here, let's see where my pen is. Hopefully I found it somewhere. So let's see here. Yeah, good. So this is my input here, and I'm going to be doing a left to right scanning of this one. So this is an LR algorithm. And you will see sometimes in parentheses some sort of a number like LR1. This would indicate the look ahead buffer. So you can look ahead one at a time. So if you are currently processing this one, you may be able to actually look ahead for the next input and so forth. So LR1 is saying that actually I have the current entry and I have a look ahead. So this is LR1. And L stands for going from left to right, the input. Okay. And then assuming that this is the order of the given order for us of the tokens. So if you recall, if we have a language like this, for example, begin, like a Pascal type of a language, let's say we have X assignment, let's say Y plus Z, and Y assignment, let's say X, and an AND. This is our raw form of the program in ASCII characters. Our lexer will go and give us a tokenization of this one. Perhaps the tokenization could be begin and let's say an ID. Let's say here this is an ID, an equality sign, and an ID again, a plus sign perhaps, and then a literal, a value, let's call this a value, and then let's say semicolon, and so forth. So this is our tokenization. This was what we discussed earlier, a week or so ago. So after this tokenization, now I can actually do concrete syntax check, assuming that, for example, I am actually doing a syntax check for this one. Of course, my CFG will be different than what I have here. Perhaps for this CFG, for example, I might have a program this is a program, the production rules, a program, let's call this with a dollar sign indicating this is a non-terminal symbol. A program is actually a begin symbol, terminal, and you see a list of, let's say, statements. Let's call this a list of statements. This is a non-terminal, and then an AND symbol, and this is an AND, right? So this is one. Okay, good. And then we have this list of statements. List of statements could be perhaps a statement like this, and perhaps followed by a semicolon. And it could be, or it could be a list of, let's say, statement followed by a semicolon, and then another list of statements and another, perhaps like this way, right? So this is saying the second rule is a statement followed by a semicolon and a statement list, right? And then we can say a statement could be, let's say, an ID, an equality sign, an expression perhaps like this, and an expression can be, let's say, an ID, a value, an ID plus an operator, perhaps, and so forth. All right, so this could be something like this. Now, the input, this particular input, when we say we are actually going to be processing this or parse this from left to right, we mean to start from the beginning and go to the end. So this is the left to right, let's say, parsing of the input. So this first L in our algorithm naming stands for or represents the order of which we actually do this one. It could have been the other way around. It could have been starting from the right one. Then it could be our, for example, L algorithm or our R algorithm. But we are not interested in these. We are interested mostly with the left to right, because this is kind of the natural order that will, with which we look at our input or our program. All right. So let's go back to the original thing again here. Now, this algorithm says you can do a shift. Shift is when shift is possible when you actually take your input, the current input, wherever your current input is. In the beginning, it will be the beginning of the thing, and then it will move on, of course. And then you just push this on top of the stack. And you see when the thing is empty, the parse stack is empty, this is probably the only thing that you can do. The reduce thing is another operation that you can do. Reduce says if you have, so you look at the top of your stack, and then if you can find a handle to replace your thing with a left-hand side of a production rule, you do it. This is what the reduce operation says. So you have two possibilities. You can do a reduce or a shift. Now, there will be cases that you can only do reduce. There will be cases that you can only do shift. And there will be probably cases where you have a conflict between a reduce and shift. You could do either of them. And there may be cases where you can actually do two different reduce operations. All right. So these are the conflicts. We are going to look at that. We are going to look at that again, but assume that there is no conflict. When does this happen? When there is no conflict, it means that this algorithm can parse an input using the particular, let's say, CFG without any ambiguity. All right. Okay. So what we do then in that case, we start with empty stack, and then we end with either a stack that actually has only our start symbol. This is a success case when there is no input left. There should be no input left. If there is still an input left and you actually end up with, let's say, the start symbol and you cannot do anything else, that might be an error case, or there might be other cases where you cannot actually do any shift or reduce. But just in that case, the only option is if you cannot accept it, and if you cannot actually do a shift and a reduce, that means that you are stuck. And if you still have if you still have things on the stack other than just one entry start symbol, and if you have still input, or you have still input, then you'll have an error case. So for this example, you see that it's very simple. You start with empty stack. And in the case of empty stack, the only thing that you can do is a shift operation. All right. And then now you have on top of your stack there is an ID. Now the question is, can I do a shift or can I actually also do a reduce? And you can see that you can actually do reduce. How? You can say that there is a rule that actually takes this ID and you can replace it with F. All right. So now you have, of course, this look ahead. That is a possibility. This look ahead tells you that actually, if you actually do a shift, then you'll have an ID plus, and the ID plus will not happen in any of the input here. Therefore, you cannot actually change this. You have to actually move on. So the algorithm, in this case, will actually do a reduce because of the look ahead, and so forth. So it's a very simple algorithm. Again, it will only work in with certain CFGs. It's not going to do all the CFGs. And the reason is the conflicts, possible conflicts. We talked about generic shift reduce problem, or the, let's say, shift reduce conflict. And then we also talked about reduce conflict. And we know that the source of conflict can be coming from an ambiguous grammar, or it can be also coming from a non-ambiguous grammar as well. And in that case, the only thing that you can do is if you have a conflict like this, you have to have some definitions going into place so that your algorithm knows how to behave. So you say, okay, if I have a shift reduce conflict, let's say I do a shift here, or I do a reduce here, or if you have a reduce conflict, I will take this reduce first with respect to, in this case, rather than the other reduce. And this is going to happen mostly in expressions, because these are going to be syntax-wise the most, let's say, complex things that you'll do. Associativity and so forth will actually show itself as a potential source of these reduce conflicts. In these cases, you actually perhaps either change your CFG such that you force those things to disappear from your, let's say, from your instance of the language, or you actually define a certain, let's say, exceptions. And we are going to talk about those exceptions in a few minutes. So removing the ambiguity, you can actually define a distinct non-terminal symbol for each operator in the case of, let's say, expressions. And then you can force the precedence of these operators, which level of precedence will take. And then you can do you can define a right-hand side of the production rule to enforce these proper associativity. So these extra non-terminal symbols can actually go for, let's say, some smallest sub-expressions. So for example, this guy, this expression goes to expression plus expression, and expressions times expression is an ambiguous one. We know that because there is a associativity that is not defined. It can actually take A plus B times C in two different ways. Now, in this case, what you can do is you can take a non-terminal symbol. In this case, I'm actually introducing another non-terminal symbol here. And what we are doing is we want to actually say, okay, if you want to, let's say, take plus to be level of precedence one after the other one, then you take this part for this guy, and then you say, okay, what I want to do is I want to actually make this early, make this happen, or take precedence than this one. So in this case, you say, okay, you go to E expression goes to expression plus some temporal thing. It's a non-terminal symbol. And then you say, okay, this terminal symbol has to be T times F. And then F is, let's say, either this one, or this one. Now, what this does is it actually already pushes you to define a associativity level or precedence level for this guy. It says, okay, this guy will take priority. This will come first, because then when you have E plus T, you know that E can go further, but this T has to be resolved. And there is if there is a B times C there, it's going to actually take that in. Similarly, you can do this for, let's say, this guy, and perhaps for multiplication as well, or the division as well. So this is like one way of doing it. Of course, there are some, let's say, there are algorithms you can try to remove these type of ambiguities, but they are not actually generic algorithms. It doesn't always work. So this suggests that kind of designing a CFG that is unambiguous is a reasonably difficult task. So sometimes because of that difficulty levels, you might force your, let's say, syntax, concrete syntax, to be, rather than this, to be something else, or vice versa. So this will force you to actually make choices. If you want to make your algorithm simpler, for example, if I want to use shift-reduce algorithm for your concrete parsers, then you may want to actually force a, let's say, more complex or a different CFG or different syntax than you want to have. So this is a choice that you have to make as a designer of your language. And you can see that this is an ambiguous grammar. It will actually lead both leftmost and rightmost trees. All right. So let me see. I'm not going to go into the. So as I said, you can. Most of these, let's say, ambiguities happen in several places. One place that people often see this is actually the operator associativity in expressions. Another one is, for example, you will see in some statements like if statements, for example, you'll see these type of examples. And there are some known examples of this, and you may also discover, depending on specific concrete syntax that you're actually introducing, you may also discover certain things. But most probably, by now, people will have actually tried a lot of different ways of defining the concrete syntax. So it's very, very unlikely that you come up with a, let's say, a completely, let's say, original and non-tried, unambiguous concrete syntax or CFG that actually leads to a new grammar or new grammar, but new, let's say, concrete syntax. So most of these have been quite a bit studied in the past. Again, one example is operator associativity. We have seen examples of this. So you see this in right associative exponentiation as well. And then another example of this one is dangling else ambiguity. You know this problem. If I have a statement, an if statement like if expression then statement, or if expression then statement then else statement, the question is, if I have an instance of this language like this, where if x less than 0, okay, this parenthesis is in the wrong place, it has to be here, and these are supposed to be here. So if x is less than 0, then you have another one. So you have this one. You have here, this guy here, this is another statement. If y is less than this, the question is, where does this else belong to? Does it belong to, I'm not doing then here, so then is not there, but does this else belong to the first if or the second if? This is called the dangling else ambiguity. We have seen this in C, if you recall, and you might have seen this in other languages. Now, the question is, what do you do in this case? So there are two possibilities. One possibility is you can actually, let's say, introduce extra symbols to make this unambiguous, right? So how could you do that? You can force these, let's say, each of these statement blocks, whatever these are, you can force them to be in blocks, for example. And then you can delimit those blocks, which some languages do. Or you can say, okay, I want to have some account. Are there any questions from the online attendees? All right. So let's see. So your conceptual, or let's say your syntax, you might have some concrete economy in your concrete syntax. You might say, okay, I want to deal these things with as few, let's say, symbols as possible. Meaning, I want the programmer to actually write as fewer symbols as possible to actually write a program. Okay, in that case, you don't want to have a begin and an end block, let's say, thingy. Then you want to stick with this one. Now, if you want to stick with this one, what you need to do is you need to actually make sure that your program your algorithm that parses this generic algorithm that parses this is able to actually parse this uniquely or unambiguously. In that case, you have to actually insert exceptions when this happens. So, like, for example, this dangling else ambiguity has a solution. And you can see that in the earlier days, people didn't want to actually put extra stuff there. Why? Because we are talking about 60s and 68, 70, and so forth, where you don't have these luxuries of today's, let's say, IDs and memories and so forth. So any character, any, let's say, bit of thing is going to be actually quite important, quite expensive when you actually force the user to take actions, right? So if you want to actually delimit these statements with certain, let's say, extra characters, that would actually make the programming difficult in those days. These days, probably not so much. I mean, you can see this already in, for example, Python. Python will actually use very, let's say, restricted or restricting syntax, concrete syntax, to actually handle a lot of these type of ambiguities. So algo 60C, C++ actually associate each else with the closest if. This is a possibility, and you can actually do this one by, in this case, you are probably saying that you will do a reduce as soon as you see that one. So when you actually do a reduce as soon as you see something like this, that will probably associate the thing with the closest if. The else statement is going to be associated with the closest if. Or you may actually want to put a, let's say, the algorithm. You can say, okay, hey, if you actually find a reduce conflict or some sort of a conflict, and I'll tell you, okay, in this type of conflicts, I'm going to check what the conflict type is. If it involves an if, I'm going to actually say, okay, associate this with the first else. For example, do a reduce here instead of shift, or do a reduce here, the first reduce here instead of, let's say, the second reduce, and so forth. Algo 68 and Modula, they use an explicit delimiter. You can see from Algo 60 to 68, already some progression of things, right? So 60 doesn't do it, 68 does that. Why? Because 60 says, 60 is, you don't probably, you start having transistors, and most of your computers those days would be probably vacuum tubes. And then 68, perhaps the things are getting a little bit better. So you have a little bit more memory, perhaps, and or maybe people learned a little bit more how to actually write code faster and so forth. So they are actually starting to use these explicit delimiters to define where the first if ends, using for example, end if statement or end if, let's say, terminal. Java rewrites the grammar and restricts what can appear inside a nested statement, nested if statement. So it says, okay, if then statement, it has an if then statement, and it has an if then else statement. So it has actually two different rules to define, or two different statements. Treats it as a two different statement, and it shows the dangling else ambiguity that way. So removing ambiguity, there is a lot of research in this one. This is not that interesting for us, but just to for you to know a few words. One algorithm or one technique is to actually factor. So factoring is you take your ambiguous grammar like that, if B then else, statement if B then else, you factor it such that you generate another statement like Z, and or you partially introduce another non-terminal symbol and actually define a rule to factor these things into the ambiguity part, into the two parts, so that those parts actually doesn't have the ambiguity that you have. So the other one is substitution. You actually if you have a rule that actually a B production on the left-hand side, like this, you actually take a goes to B alpha, and you replace all B alphas with that A. This is called the substitution method. And then some grammars actually have, we are going to see this one when we talk about extended BNF, they use some meta symbols like curly braces, parentheses, and so forth. Now, we have talked about these grammars in the Chomsky's hierarchy, and we dealt with two of those. And one of them we dealt with quite, let's say, exhaustively, the regular grammars. And generic context-free grammars are not necessarily algorithmically easy to solve or algorithmically easy to parse. So we limited that to, let's say, simpler versions where we can, let's say, use an LR1 or LL1 or LR2 algorithm to actually parse these things. There are, of course, more powerful grammars like this. When you have a production rule which has a left-hand side that doesn't have only one terminal symbol or non-terminal symbol, sorry. So it may have more than one terminal and non-terminal symbol. So this is a production rule where you have at least one non-terminal symbol on the left-hand side, but on the left of it and the right of it, you might have more than one terminal and non-terminal symbols. And decision on this type of problem is what is called p-space complete. And let's say, for example, the emptiness, checking of the emptiness of a language in this case is the undecidable and so forth. So these are difficult problems. You may not be able to solve these in many cases. And then if you have no restrictions at all, then you have a equivalence to Turing machine. So in terms of the grammars, you have the way that we use grammars in this case is different hierarchies. Now we are going to actually invert it. We gave you a kind of a, let's say, hierarchy where the expressive power of the grammar actually grows from regular grammars to context-free grammars, from that to context-sensitive grammars, and from that to recursive or enumerable, whatever, grammars. Now, what we are going to do now is when we look at actually a program space, so your lexer through a regular grammar will take any combination of, let's say, characters, ASCII characters, which is going to be, let's say, this space here. This is, let's say, assuming that you have n characters in your program, potential program. So you have n characters, n could be 1, and could be infinitely many almost. Okay, so there will be no infinite here, but you can think of this as big as you can get, right? So in this case, the space of all programs is, so if you are using, let's say, ASCII characters, you have 256 characters, and then you have this many 256 to the power n possible configurations of these characters to actually to generate. So you can generate 256 to the power n different programs out of this. So if you, for example, if this guy writes a program that has, let's say, 100 characters in it, then in principle, we might be able to actually organize them this many different ways to as a program. Okay. Now the question is, okay, of course, this number is a big number. Cannot enumerate these numbers easily, not probably ever. But the question is, we know that all of these different combinations of characters are not going to be an instance of my language. They cannot be. Right? For example, for C, I know that if I have 100 characters, C, for example, will not take, let's say, this one, let's say something, 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 let's say 1, 2, 3, X, Y, Z. This is not going to be, assuming there is a space here, white space here, and there is a white space here. C will not take this as an instance, regardless of what the others are. Why? Because this doesn't actually pass the regular expression defining the lexer. So this entire space of things here is actually limited within this one here. Now you know that this is still big. This is not everything that actually passes this is still your language, right? So for example, an example could be, let's say if I have a main function, if I have something like this, x is, let's say, I don't know, let's say even though it is passing, or something like this, let's say equality sign x plus y, right? This passes the lexer, because from lexer's perspective, these are all good, right? This is an equality sign, this is a ID, this is an operator, this is an ID, this is a, let's say, a punctuation. All right, fine. But from the concrete syntax perspective, this is not correct. This is not a statement or an assignment statement, because assignment statement requires something to be defined, an ID to be defined on the left-hand right of the left-hand side of the equality sign. So this is going to be done by the concrete grammar, or concrete syntax is going to be defined by our context-free grammars. Okay, now I have this regular grammar restricting my space, and then now I have even whatever passes this regular grammar will be constrained within this one by the context-free grammar. So not all the instances that passes the regular grammar is going to be an instance of that language. That is not going to be still sufficient. We know that. Why? We can see that, for example, even if I have something like this, let's say I have x assignment x plus, let's say y, something like this. I know that this is going to pass my first lexer, because I have nothing wrong with the lexeme here. This will pass my concrete syntax. There is nothing wrong with the actual concrete part of the syntax here. This passes the actual concrete syntax, meaning the syntax of that expression is true, correct. But there is also, I have a problem here. This is not going to be an instance of my program. My compiler is going to reject this. Why? Because it may be that the y and x might not be actually the right type. Y could be, for example, a string, and x could be an integer. If x is an integer and y is a string, then this guy is not going to add them together. Okay. Now, this is defined by mostly context-sensitive grammars. And they don't write it this way because we've seen that context-free grammars are not actually algorithmically, let's say, solvable always. Therefore, you'll have these type checkers. We call them type checking. For example, is going to be an example of it. In some languages, it could be something else. That will actually even further shrink the space of acceptable combination of those characters, right? So some of them is not going to be, because you can see why this is called context sensitive, because this particular thing passes my, let's say, parser, but there is somewhere else, there is a context that defines what this is and what this is. And that context actually lets me know if this guy is correct. All right. So that's why it is called context sensitive. Sure.
Is this statement can pass from context sensitive or not?
So we don't know if it is context. So first of all, is it context sensitive? Depends on actually how you look at it, right? So when I look at it this way, from a, let's say, a CFG perspective, I can probably write this as a context sensitive, with a context sensitive grammar. Why I think it is context sensitive? Because without actually knowing some things that is happening prior, or maybe depending on the language also, if you have a dynamically set up let's say type language, you might also need to looking up actually downstream and upstream. So the context of what is happening here is going to define this guy. So for example, if you have a dynamic typing system, and the type of this thing is decided somewhere here, then let's say a left to right parsing of this thing is never going to happen, because I have to decide it here, but the decision is depending on the context that is actually happening later on. This is one thing. In the other case, even if it is actually happening here, I have to keep a memory, which with the algorithm that we have seen, you can see that I didn't need to do any memory. I was just looking at my current input and the one look ahead and whatever is happening on top of my stack. So that is not context, and that can only go until the end of let's say a production rule. Here, you might need to actually look at a completely different set of production rules to decide what this guy is going to be. So, for example, you might have a production rule for variable definition in an imperative language, and then you might have a statement set of production rules for statements, and there has to be a interaction between these two in place and perhaps in time. So this is the context sensitivity. So this means that whatever you do, you cannot actually do this. I mean, let's say, in some cases, these context-sensitive things cannot be actually ever represented in a context-free grammar. Therefore, you have to change your strategy for this type. And what will happen is that we are going to move away from grammars, these meta languages, and we are going to actually do this as we usually do. We are going to do this with writing, natural languages. Yes.
Production rule in these things.
Say it again.
Production rule. You know, we have sets in the regular context.
So BNF can be used here. Simple. Usually we don't even use this BNFs. We use here regular expressions. And BNF is going to be used here, the Buckles-Naur form. Here, probably not. Okay. And then even this is not going to be actually the code is going to be correct or is going to be instance of your program, because even if it actually passes all these things, it may still not run. At runtime, it can actually generate errors. And there is no way to actually define these in a grammar. So our grammar approach will only help us very well with this part, somehow with this part, still well enough. But after this, there is no way that we are going to be able to actually kind of systematize this thing in a nice manner. Yes?
For example, if I'm writing C code,
yes.
Let I integer plus string for C, just I'm saying for C.
Yes.
Context sensitive, say this is true or not.
Context, okay, type checker is going to say that, okay, we are saying that in principle you can define this as a context sensitive grammar, but we are not going to do this because context sensitive grammars are not going to be parsed easily. Therefore, we are going to say, okay, even though you can actually describe this with a context-free grammar, the difficulty of it is going to move us from that, and we are going to say, okay, let's just write the algorithm for it. And the algorithm, we are going to write it by ourselves. So we are going to see simplified versions of it. Now, if you are asking, is there a possibility that I can write a context-sensitive grammar for this one? Perhaps you can. The second question is, can I hope to have an algorithm that can parse that? Probably not. Okay, does it make it clear? You still have questions, but ask me again. Right? So even with the correct program on runtime, there is no such thing at all. So the reason that I'm actually giving you this picture is that even with the idea of this nice, let's say, meta language that can define our intention, the semantic, with another language holds up to a point, and after that, you are on your own, meaning we are going to use our, let's say, engineering skills to actually solve the rest of the problem. All right. Questions? So what will happen is that if you are, let's say, if someone designed, or if if someone comes to you and say, okay, what's your name?
Salih.
Okay, someone says, Salih, I have a new platform. I want you to actually implement C for a C compiler. All right. So Salih probably already knows that there is a BNF or a regular expression, set of regular expression to define the lexer. Okay. What will happen is that he's going to take that. He's going to take that lexer, BNFs, or call them, let's say, for the time with BNF. You can do this with BNF or regular expression. And there is a thing called probably, let's say, flex, a C code that can take this guy and actually give you another C code, let's say, right? Now, he got this one already done, and this is ready. So this algorithm here is a generic, actually this is a program. It's an executable. It takes your BNF and it actually generates the C code to generate your tokens. Right now he has the first part, this one. There is also this part as well for C. Someone has written it already. So he's going to take the second part of BNF. This is now concrete syntax. Concrete syntax is not as simple as this guy. So this is a regular expression, and this is this context-free grammar, right? So this algorithm is never going to solve it. But there is an algorithm, there is a program very similar to this one. Let's say Yak or Bison or whatever. So let's say take Yak. This is another one that actually does for a set of context-free grammars, not all of it. You can actually take the BNF and generate another C code. Okay, this is an executable program. He's going to feed in BNF and he's going to receive a C code. All right. Now, after this, he's going to end up with this part. Okay. Some of these things are going to be handled by Bison. Right. But then the rest of it is he's going to take the C code and he's going to actually edit and update and not rewrite, perhaps sometimes rewrite and add code to this one to implement this part as well as this part. This is how it goes. So this is very powerful. If you needed to actually write this one, which will be a homework for you, this part is quite perhaps easy, but you are going to write it. This part is not that easy. And then now this is saving you from writing it. But again, the classes of BNFs or classes of, let's say, instances of, let's call it this way, instances of the CFGs that you can handle here is not going to be infinitely many. It's going to be limited. But still, when the C people designed this one, they actually knew this. Therefore, they designed this part such that it can actually use Yak to actually do that. Now, think about it this way. Assume that you don't like to actually use C because you are writing a C compiler for your stuff, and you don't have a C compiler, but you have a Java compiler. So what happens is that people go and actually take a Lex or a Lexer and a Yak or whatever, and get there's a Java version of this. Java version of this guy is going to be JLex, and then there is another version of this one. I don't remember right now what it is, but you would have that, and then now you'll generate the Java code, and then you'll update, rewrite, re-edit, and all these things to actually generate the rest of the actions here. All right. Now, the semantic analysis on top of concrete syntax is going to be our next topic, and we are going to spend a lot of time on this one. When we talk about semantic analysis, we are now talking about what is our statements doing? What type of actions are they generating? Expressions, functions, program in general. What is it going to do? How is it going to do things? Depending on actually the former, the lexer, and as an outcome of the lexer and the parser. So this goes beyond the context-free grammar. Things like this, for example, is X declared before it is used? I need this information. is an identifier declared before it is used. You cannot actually define this as a context-free grammar. For example, is X declared but never used? You can write this one easily, perhaps, right? So it's not a big deal. If I want to actually put this as an algorithm, so I say, hey, what is the deal with this one? I'll take my IDs, and whenever I see an ID, I say, okay, have I seen this before? This is gonna be the scope. And we are gonna say that, okay, if we have a scope that is actually defining this variable, which I can actually, let's say, do it on a stack or a, let's say, linked list structure or whatever. But what I am doing is now I am actually associating my semantic with an algorithm that I would write by hand. There is no meta language to define it now. Like if X is declared before use, why do I care? I run my entire thing, and at the end of the compilation process, I go with, for all my variable definitions, I say, okay, have I ever used this anywhere? And then I can easily check them. But that easily checking means you have to have a specific algorithm. This is not going to be done by a, let's say, a meta language, which will have an algorithm that parses that meta language or instantiates that meta language. Is an expression type consistent, for example, or is an array reference out of bound? Some languages doesn't even do this one, right? We know some languages like C doesn't check if an array reference is out of bound. Some languages do, right? So these are semantic, part of the semantic of an array, of a variable, of an expression, and so forth, that cannot be captured by a context-free grammar. So what do we do then? How do we do this one? Okay, there are several options. One option is we use context-sensitive grammars. Okay, we said we go beyond the context-free grammar, but we still want to use context-sensitive grammars. The problem with this approach is it will be hard to define and costly to use. All right, you have to write all these exceptions and so forth. So it may defeat the benefit, defeat the purpose that you would actually use a context-free grammar at the first place, right? And people usually don't do this. The second approach is you can use another grammar, and we'll call this an attribute grammar. And this is not going to be, let's say, a kind of a, let's say, a magic wand that you can actually solve every problem with, but it is a useful tool. It's a simple tool. It has been used in the past. We are going to talk about this a few, let's say, today. Oh, I'm already out of time. And this can help at some extent, but not necessarily it will solve every problem that we have. So what is remaining? The remaining is ad hoc methods. We say, okay, we use methods that are not, let's say, well-defined in terms of, let's say, as like a meta grammar or meta language. So Sarif will actually say, okay, I'm going to define this, and then some programmer that reads it. What's your name, for example? Dervish is going to say, okay, I can read his writing, and I can actually write an algorithm to do that. Maybe he's going to write a different algorithm to do that, but the way that we are going to handle these things is going to be actually ad hoc. And this is going to be mostly required for especially semantic analysis, like, for example, array reference out of bound. This is a very, very difficult thing. This cannot be even done at static time. It has to be done dynamically, right? Okay, let's take a 10-minute break. We'll continue with attribute grammars.